Assalamu alaikum class. I hope that all of you are well and safe in your homes inshallah. Lecture 30 of our course Signals and Systems is going to conclude our discussion of Fourier series. We'll apply the concept of Fourier series to analyze LTI systems through an interface known as the frequency response, and we'll observe the frequency response of a certain class of systems known as filters and see how Fourier series can help us to design the filters. So let's proceed. Before applying the concept of Fourier series to analyze LTI systems, here's a quick recap of what we know about LTI systems and Fourier series so far. So from lecture 27 to 29, we have seen that Fourier series can be used to express continuous time and discrete time periodic signals through a sum of harmonically related exponentials. By harmonically related exponentials, it implies that all the exponentials or the sum of exponentials which are used to represent the periodic signal are related to each other through fundamental frequency of the period or fundamental frequency of the periodic wave. We have seen that for continuous time periodic signals, there are certain conditions that need to be met for the signal to have a Fourier series, but essentially all signals of practical importance can be expressed through Fourier series. We've also discussed in lecture 18 that complex exponentials are eigenfunctions of LTI system. This implies that if a complex exponential of a particular frequency is an input to an LTI system, at the output we get the same complex exponential. The magnitude and phase of the complex exponential might be modified, but the frequency remains the same. So, and how is the magnitude and frequency of the input exponential modified by the LTI system? Is through the system function, which means that if for this LTI system h of expressed through the impulse response h of t, if the input is x of t is es of t, then at the output we get the same exponential, complex exponential es of t, and it is multiplied by h of s, which is the system function of the continuous time system. S is a complex variable which has a magnitude as well as a frequency as well as a phase. This exponential can be expressed in polar form as say a magnitude s, real s, and phase of s. However, we plot this s in complex plane using x-axis and y-axis representation. Similarly, for a discrete time LTI system expressed through the impulse response h of n, if the input x of n is the exponential, complex exponential z raised to the power n, at the output we get y of n is equal to z raised to the power n multiplied by h of z, where h of z is again the system function of the discrete time system, and z can be expressed as r e j omega. This is a polar form, which means that r is the radius of the rotating exponential e j omega, because e j omega has a magnitude of 1. Omega represents its phase and r is the radius of this rotating exponential. We will not go into too much detail about how we plot this vector in the z-plane, because you will discuss this in your course DSP. Currently, for signals and systems, it is sufficient for you to know that z of n is also a complex, or z is also a complex variable and can be expressed in a z-plane through a radius and a phase. So I have taken the liberty to duplicate slide 8 of lecture 18 to see what is the response of an LTI system to an input sum of complex exponentials. Suppose that our input is expressed as a sum of complex exponentials of different frequencies. Then, since we know that complex exponentials are eigenfunctions of LTI system, the output with respect to input A1 E S1T will be A1 H S1 E S1 of t, where H S1 is the system function evaluated at frequency for this E S1 of t. The magnitude of H of S1 will be multiplied by A1, and the phase of H of S1 will add to the phase of S1 vector. However, the frequency of S1 will remain constant. Similarly, when the input is A2 Es2 of t, the output is A2 H of S2 into Es of S2 of t, where again H of S2 is the system function evaluated at frequency S2 and so forth. So the output is a sum of the same complex exponentials having the same frequency, but they are now modified by the system function. So for both continuous time and discrete time systems, if the input can be expressed as a linear combination of complex exponentials, then the output can be represented by a linear combination of the same complex exponentials. So this concept is going to be applied to analyze LTI systems using Fourier series. When S or Z are general complex numbers, H of S and H of Z are referred to as system functions of the corresponding continuous time and discrete time systems. To analyze the frequency characteristics of systems, we'll focus on a special case for which, for example, for continuous time systems, the real S is 0, so that now our S is equal to j omega, and E of st takes the form e j omega. So now when we analyze the system function and take its Laplace transform instead of the variable s, the Laplace transform is a function of omega only. So h of j omega viewed as a function of omega is termed as the frequency response and defined as h of j omega is h of t into e raised to power minus j omega t integrated between the interval minus infinity to plus infinity. We can see that over here this expression is similar to the Laplace transform expression. The variable s is replaced by j omega because sigma is 0. So the frequency response is the situation for a continuous time system when for the variable s, sigma is equal to 0 and only omega is existing. Similarly, for discrete time systems, we'll be focusing on the values of z for which z is equal to 1. So again, now z is equal to e j omega and z of n is of the form e j omega n. So now h of z or the system function becomes h of e j omega and is termed as the frequency response of the system. This is given by h of z is h of n into e to the power minus j omega n, and you sum it from n is equal to minus infinity to plus infinity. This expression is a discrete time counterpart of this expression, and again you will discuss or determine this expression a lot in your course TSP as well as the forthcoming lectures about Fourier transform. So I introduced the variable z in slide 1. In fact, slide 2, because slide 1 is generally introduction slide. So this is a plot of the situation when c is equal to 1, real c and imaginary c, and since we plot c as a rotating vector which has a magnitude and a phase, so now the magnitude is 1 and this omega is the current location of the vector. It could be here anywhere, but this is just to show that if you're plotting r, e, g, omega and r is 1, then this situation, this vector depicts this situation. Now x of z was defined everywhere on this plane, but x of e, g, omega is defined only on the circle with r is equal to 1. This unit circle is also known as a unit circle because it has a magnitude of 1. So combining these two concepts, what is the response of a continuous time LTI system going to be when it is subjected to a periodic input? Suppose that x of t is the periodic signal with a Fourier series representation given by x of t is equal to a of k e j k omega naught t, and k varies from minus infinity to plus infinity. This slide is from your book, so I'll be using the book equation number. So this is equation 3.123. Now when we apply this signal as an input to an LTI system with impulse response h of t, each of the complex exponential will have a corresponding output, and therefore our output y of t can be expressed in the form y of t is ak h jk omega naught into e jk omega naught t. Now you can observe that in the previous slide I had used h of s1, but now since our s1 is a function of j omega only for the frequency response, so we term it as h jk omega naught, where k, for example for a of 1, this k will be k of 1 and this complex exponential will have j omega naught t. Similarly, for say k is equal to minus 2, this will be a of minus 2 h minus j 2 omega naught into e raised to power minus j 2 omega naught t. So y of t is going to be a same sum, but this is now being multiplied by h jk omega naught. So y of t is also periodic with the same fundamental frequency as x of t, and if ak is the set of Fourier coefficients for x of t, then the set of coefficients for y of t is ak h jk omega naught. So what is the effect of LTI system on the input? The effect of LTI system is to modify individually each of the Fourier coefficients of the input through multiplication by the value of frequency response at the corresponding frequency. So h of j omega will be evaluated at each frequency, and this frequency response will be multiplied by the coefficient c of k. This is going to be illustrated through an example in the upcoming slides. Similar to the continuous time case, for a discrete time LTI system, when it is subjected to a periodic input, the response, the output is going to be the same. So if the discrete time periodic signal is expressed through a Fourier series given by this equation, where we remember that for a discrete time case, Fourier series is periodic with a period n, which is the same as the time period of the discrete time signal. So if this signal is applied as an input to a system, LTI system, then the output y of n is going to be a of k into frequency response at ej2 pi k by n, where k is going to vary over the entire time period. You can vary it from minus n by 2 to n by 2, or you can vary it from 0 to n, that is your choice. You must remember that the summation varies over n multiplied by the input exponentials. So y of n is again going to be periodic with the same period as x of n, and the kth Fourier coefficient of y of n is the product of kth Fourier coefficient of the input ejk 2 pi by n into small n multiplied by k, and the value of the frequency response of the system h ej2 pi k by capital N at the corresponding frequency. This parallels the discussion for a continuous time case. Now let's solve an example to illustrate this concept further. This is example 3.16 of your book. We have to determine the output of a system given the impulse response h of t is exponential of minus t u of t. We can see that since this impulse response is being multiplied by u of t, which means that it will exist from 0 to infinity only. The input of the system is given by x of t is 1 plus half cos 2 pi t plus cos 4 pi t plus 2 by 3 cos of 6 pi t, where 1 is the DC component and these are cosine waves at 3 different frequencies. So to solve this question, first of all, we have to see whether x of t can be expressed in the form of an exponential Fourier series. When we look at this input signal, we can see that this input is a sum of 3 cosine waves, and the fundamental or the basic period can be seen as omega naught is equal to 2 pi. So this is the DC component, this is the fundamental or the first harmonic, this is the second harmonic, and this is the third harmonic. So if I open this expression through using Euler's formula, I am skipping a step because I assume that after applying Euler's formula so many times, you know it by heart. So I'm just opening this and rearranging the terms. We'll have x of t is 1 by 3 e to the power minus j 3 into 2 pi t, which is the component coming from negative exponential for this term, plus half e minus j 2 into 2 pi t plus quarter e to the power minus j into 2 pi t, which is coming from this expression, plus 1 and plus positive exponential for all these terms. So x of t can be given as this form after expansion of the input terms. So from the previous slide, we have seen that x of t can be expressed in the form of a Fourier series. And we have described that when x of t is expressed in the form of a Fourier series, the output y of t can be given as y of t is equal to summation of k from minus infinity to infinity, a of k multiplied by h j omega k omega naught into exponential jk omega naught t. Now this h jk omega naught is the frequency response evaluated at each of the frequencies given in the input. So we have to know what is h j omega naught. The expression for h of j omega naught was given in one of the previous slides, but I'll show how to derive it in case you've forgotten. How did we determine it? We remember that h of s was given as h of s is equal to minus infinity to infinity x of t exponential of minus st d of t. Now for frequency response, we replace s by j omega. So h of j omega becomes h of j omega is equal to minus infinity to infinity x of t exponential of minus j omega t dt. So we are integrating x of t from minus infinity to infinity by multiplying it with exponential minus j omega t dt. I substitute the expression for input. Since input was defined from the interval 0 to infinity by virtue of being multiplied by the unit step function. The limits are modified and we get h of g omega is equal to e exponential minus t into exponential minus g omega t dt. When we integrate this expression, we get minus 1 by 1 plus g omega into exponential of minus 1 plus g omega t, and after substituting the limits from 0 to infinity, h of g omega comes out to be 1 by 1 plus g omega. Now this is the expression for the frequency response of the input for the system given to us, and we'll have to evaluate this frequency response at each of the frequencies of the input to determine the output through this equation. Let us denote the product A of k into h jk omega naught as B of k, or we can say that B of k are the Fourier series coefficients for y of t. H jk omega naught is going to be evaluated for each of the terms, each of the frequency terms in the input. X of t is being rewritten over here, and we remember that when x of t was expressed in the form of a Fourier series, this coefficient was a of minus 3 because this was at third harmonic and this is minus j3. Similarly, this coefficient is a of minus 2. This coefficient is a 1 by 4 is a of minus 1. This coefficient 1 is a of naught. 1 by 4 is for a of 1. 1 by 2 is for a of 2. And 1 by 3 is for a of 3. So B is going to be determined at from minus 3 to plus 3, or for minus 3, minus 2, minus 1, 0, 1, 2 and 3, which are the same frequency terms as the input. So B naught is A naught into frequency response evaluated at 0 frequency. From the previous slide, we know that frequency response h of j omega is given by 1 by 1 plus j omega. So we'll replace omega by 0 and we get 1 into 1, which is equal to 1. So the coefficient B naught is 1. The coefficient A1 is the frequency response evaluated at J1 into omega naught, and omega naught is 2 pi. So in the frequency response expression, we'll replace omega by 2 pi. Once I solve it, I get 0.0393 into a phase of minus 1.4123 radians. I have used MATLAB to determine this expression. Your book has just limited it to this factor. The phase can be expressed in terms of a multiple of pi. If you can divide this phase by pi, so the result will be in terms of pi, but I think expressing phase like this is sufficient. It is not a necessary condition to express the phase in terms of, say, pi by 4 is 0.25 pi. You multiply 0.25 and 3.1416, which is pi, and the answer is okay because all of this is expressing a phase. Now B of minus 1 is A of minus 1 into h of minus j 2 pi. So now we replace frequency minus j 2 pi in the frequency response and evaluate the expression, and we get this term. Similarly, we determine B at all the frequencies at plus 2. So for plus 2, our phase or frequency factor term is 1 by 4 the frequency term is 4 pi now. So we'll replace omega by 4 pi over here. For A of minus 2, we'll replace omega by minus 4 pi. For B3, we'll replace it by 6 pi, and for B of minus 3, we'll replace it by minus 6 pi. We determine the magnitude and phase of the resultant expression. This phase can also be written as, for example, this phase, this is 0.093 e raised to power minus j 1.4123. So in the resultant expression, I replace for y of t all the bk coefficients and I add them, and once we substitute the value of all the coefficients, we can see that the coefficients for positive frequencies are the same as negative frequencies, however the phase is different. So I group the like terms together like this and bring them into the same form, convert them into cosines by using Euler formula, and bring the answer in the same form as the input. This final step is not necessary. In fact, giving your answer till this point is sufficient for all discussions, but I just simplified, or I just grouped the terms together to illustrate the same concept, that the output is the same sum of cosine terms as the input. They are just modified by being multiplied by a magnitude factor, and the phase is adjusted, and both this magnitude and phase comes from the frequency response. We see that although we multiplied complex exponentials, the output is real because the input was real. So if you give a real input, you get a real output. So we have seen that how the frequency response can be used to determine the output when the input is a periodic signal. In the last example, we have seen how to determine the output when the input was a continuous time periodic signal. Example 3.17 of your book discusses the situation when the input is a discrete time periodic signal. Similarly to the case of continuous time signals, for the discrete time signals, you'll proceed the same way. Now, frequency response is not just used to determine the output. Frequency response of a system is one of the most useful characteristics of the system because it tells us how the system behaves when it is subjected to signals of different frequencies. So based on the response of the system to all these frequencies, we can classify what sort of a system we have. Now, one of the most important applications of signal processing is filtering. What is filtering is, perhaps for an input signal, we want to change the amplitudes of all the frequency components, or the signal is contaminated by, say, some noise, and we want to eliminate that noise, or we want to enhance a particular frequency component of the signal. So all this is achieved through the process of filtering. So LTI systems that change the shape of the spectrum, that is, which work on all frequency components, are known as frequency shaping filters. Whereas systems that are designed to pass some frequencies and stop other frequencies or eliminate those are known as frequency selective filters. So as we discussed, that the Fourier series coefficients of the output of an LTI system are those of the input multiplied by the frequency response. So filtering can be accomplished using the LTI systems with an appropriately chosen frequency response. The frequency response of the system is such that whenever it is subjected to the input, the kind of an output we want, we can achieve that through the frequency response. The frequency domain methods, that is Fourier analysis, provides us with the ideal tools to examine this very important class of applications known as filters. So let's discuss some filters. The first in this case is frequency shaping filters. So one frequency shaping filter is differentiator. A differentiator is given by yt is equal to dx of t by d of t. If we assume that the input is a complex exponential, output y of t comes out as j omega h of e j omega t. If we are going to implement a LTI differentiator, then comparing this with the standard form, we know that h of j omega will come out to be j of omega. When we plot this response, that is, we vary frequencies from minus infinity to plus infinity, and we plot this response, we can see that this response has the magnitude of this frequency response has a form like this. As frequencies increase, the h of j omega, magnitude of h of j omega increases. The increase in magnitude of frequency response means that when an input exponential is being multiplied, the greater the frequency of the exponential, the greater will be the coefficient, magnitude coefficient that is being multiplied by it. And the lower the frequency component, the lower would be the multiplying coefficient. The phase plot of this integrator, as it can be seen, has two phases. For positive frequencies, j is positive, which means a phase shift of pi by 2 radians for positive frequencies, and a phase shift of minus j or minus pi by 2 radians for negative frequencies. Frequency response is plotted by varying frequency from minus infinity to plus infinity and seeing the magnitude and phase for each of the terms. Right now, at the current stage, we are not going into too much details into how to plot the frequency response, but you will be informed of it by the end of this course in the next section, which is Fourier transform. So what is the use of a differentiator? Well, differentiating filters are used to enhance rapid variations or transitions in a signal. In image processing case, this is also known as edge detection. That is, we want to see where there is a rapid variation in the signal. This is illustrated in the next slide. Whenever we apply a differentiating filter to an image, for example, this is a situation where we had two images, and as it can be seen that these images have certain buildings, pathways, but we are not too sure where exactly on the image they lie. So once we apply a differentiating filter to these images, now the edges of the image are very clear, very sharp. Frequency shaping filters can be used in audio systems to adjust frequency components in the recorded signal. You must have seen these cassette players, those music players, where you have certain controls and you use those controls to listen to a different sound than what is recorded. The most common types of filters which are used in audio processing are the bass filter and the treble filter. The bass filter is used to adjust the low frequency components in the recorded signal, and the treble filter is used to adjust the high frequency components. Similarly, in hi-fi, high fidelity audio systems, an equalizer filter is included to compensate for the frequency response characteristics of the speakers. The speakers have their own response, so to adjust that response, an equalizer is also used. So the overall response is all these three filters, the bass, treble, and equalizer filter, are connected together in cascade to adjust the overall output. And this overall adjustment is also known as an equalizer circuit or an equalizing circuit. shown is an illustration where three different frequency bands are being adjusted. This is an equalizer circuit, and three different frequency bands are adjusted, and the overall response is a product of all these three individual response. For those of you who are interested to explore this domain further, in your book, Frequency Shaping Filters with respect to audio systems are explained in much detail. You can look at them. This is also useful for people whose project is on signal processing, uses of signal processing in audio applications. So for the curious ones, you can see the book. The second class of filters is the frequency selective filters, which are intended to select some bands and reject others. Such filters may be used for noise removal. They are used in demodulation circuits. Remember, we discussed frequency shifting property of Fourier series and modulation. So during demodulation, frequency selective filters are used. And in common life, this is the most commonly used filtering application. For example, air filters sieve dust particles and provide you clean air. Oil filters sieve dirt particles and things you don't need, and give you clean oil. So frequency selective filters is the application we are going to be using the most in signal processing courses, which is signals and systems and DSP, that is digital signal processing. So based on the type of frequency bands these filters select, they can be classified as different types of filters: low pass, high pass, band pass filters, etc. So a low pass filter is a filter that passes low frequencies, and low frequencies are the frequencies around omega is equal to 0, and it attenuates or rejects higher frequencies. A high pass filter is one which will pass higher frequencies and attenuate the lower ones, and a band pass filter is one that passes a band of frequencies, and the band of frequencies would be varying anywhere, could be anywhere. It is selected based on your choice of parameters. So based on the frequency we intend to pass or reject, a term cutoff frequency is defined, where cutoff frequency is the boundary over where the frequencies are passed or rejected. For example, for a low pass filter, the cutoff frequency is the point till the point where the low frequencies are passed. After or beyond that point, the frequencies are attenuated or not passed. For a band pass filter, cutoff frequencies define the band. The lower cutoff frequency and the higher cutoff frequency define the band between which the frequencies are passed. Otherwise, the rest of the frequencies are attenuated or stopped. Frequency selective filters were defined as filters which pass the desired band of frequencies and attenuates or rejects the unwanted band of frequencies. Extended this definition and introducing ideal frequency selective filters are the one that exactly pass exponentials at one set of frequencies without any distortion and completely reject signals and all other frequencies. So the response for an ideal low pass filter would be one which passes exponentials in the range between minus cutoff frequency to plus cutoff frequency and rejects signals at frequencies. The response would look like this, where in the frequency response, this is the pass band and this is the stop band. We can see that by virtue of using the exponential Fourier series, we have response on both sides of the frequency, since we know that the magnitude response is always symmetric. H of g omega is defined as 1 because it exactly passes complex exponentials. It does not modify them. So h of g omega is 1 if omega is less than or equal to omega c, which is between cutoff frequency and 0 otherwise. Such a response, which has very well defined sharp edges, is also known as a brick wall response. And we'll see that this ideal brick wall response is very difficult or impossible to achieve in real life, and the response has some variations. A variation means that it might have a multiplying factor or a magnitude in the pass band, and in the frequency band all the frequencies will not be exactly rejected, completely rejected. They'll be attenuated a lot, but they'll not be completely rejected. It is impossible to eliminate them completely. Why does this happen and how does this happen is going to be one of your assignment questions for this lecture. Similarly, the frequency response of an ideal high pass filter with cutoff frequency omega c would be this one for the continuous case and this one for the discrete time case. It is clear that for the discrete time case, the response does not extend to omega is equal to infinity, because we remember that distinct frequencies for discrete case exist only between the interval minus pi to pi or 0 to 2 pi. Afterwards, the frequencies start to repeat themselves. Again, you see that the frequency response is symmetric. So a high pass filter, if you want to observe the response, you can observe between 0 to omega and say this is a high pass filter response, because this response for the negative frequencies is a mirror image of the response for the positive side, and it exists because of the exponential Fourier series that we are using to observe the frequency response. It should also be noticed that for the continuous time case, the frequencies are denoted by omega, and these are the analog frequencies, whereas for the discrete time case, again, the frequencies are depicted by omega. There are certain books which use other terms for this frequency, but your book uses the omega term. So whenever you're using omega, you must be careful to see what frequency are you referring to, whether it is the digital frequency, which is 2 pi by capital N into the frequency term, or you are referring to the analog frequency. Also, you can see that for these responses, the magnitude plots are even symmetric, and h of g omega represents the frequency response for the continuous time case, and for the discrete time case, we express it or write it as h exponential of g omega. For the bandpass filter, which is between two frequency bands, the frequency response exists between a band, so only this band is passed, and the rest of the frequencies are rejected. This is a situation for the discrete time case. We see that each of these filters are symmetric, and there appear to be two pass bands, but you can say, if novice would claim that this looks like two pass bands, but you know that these are not two pass bands, this is just one pass band if you see from 0 to omega. And as I said, for discrete time case, h of e g omega must be periodic with period 2 pi. So you can see your paper, your book, to observe the frequency response between 0 to 2 pi. I have given you the response between minus pi to pi. So the low frequencies are the ones which are near even multiples of 2 pi or 0, and the high frequencies are one which are near odd multiples of pi or 3 pi. If you are observing the response between 2 pi to 4 pi, so the response near 3 pi would be higher frequencies. In fact, in this slide and in many slides, I have placed a bookmark, a note at the bottom of the slides. In some of the slides, it's a hyperlink, whereas the rest of the slides, it's a footnote. So I hope that you look at the footnotes to see more details, what is written, and you can use that information to explore further in case you are interested to look further into a slide. The filters we discussed can be implemented in continuous time using physical hardware such as resistors and capacitors. We'll see that a simple resistor and capacitor connected in series with a voltage source can act as a filter. So shown in this figure are a resistor and a capacitor, and the output voltage is taken across the capacitor. So writing the circuit equation through voltage equation through KVL, we can write RC dVc by dt plus VCT is equal to Vs of t. If we assume that the system is initially at rest, it means that it is an LTI system. So for the frequency response, to determine the frequency response, we know that by definition our input is E j omega t, so that the output is E j omega t modified by H j omega. So we'll replace this by the V naught t or Vc of t by this term. So replacing them in the above expression, replacing input by E j omega t and Vct by H j omega E j omega t, we get this expression. And once we take similar terms on one side for the H j omega, we get H j omega is equal to 1 by 1 plus RC into j omega. So this is the response of this system. Now, what is the order of this filter? The order of the filter is the order of the highest derivative or the highest integral if the equation is an integral equation. So the order for this case, the order of the system is 1 because the maximum derivative is 1. We can plot the frequency response by varying the values of omega and observing magnitude and phase for the frequency response at each point. So plotting such a response is shown in this figure. We can see that as omega increases, the magnitude of h of j omega decreases. So such a kind of a response can be categorized as a non-ideal low-pass filter response. The cutoff frequency is at 1 by tau, where tau is equal to RC. The phase of this response is also shown in figure. We can see that for positive values of frequency, there is a phase delay, and since phase response is odd symmetric, so this is observed in the negative values of frequency. Since you are not given a value of R and C, so it is not easy to plot such a response. How can we get such a response is explained on the next slide, which I'm not going to go into detail, but you can give some values to R and C and vary omega and plot this response through MATLAB as well. We'll see how to plot this response for the next section, which is Fourier transform. So far for you, observing the general response and categorizing it as a type of filter is sufficient. If we plot the time domain, if we determine the time domain expression, we can see that h of t is 1 by RC e to the power minus t by RC u of t, and step response comes out to be this value, where step response is the response when the input is a unit step function. And how you determine step response is through convolving the impulse response with the input, which is a step function. These responses, the step response and the impulse response, are given here or shown here to illustrate a trade-off in filter design. Now if, for instance, we want to select very low frequencies, This means that 1 by RC must be very small. So if 1 by RC is very small and we achieve very low frequencies, or we pass very low frequencies, then you can see that the system reaches its steady state very late. What is the steady state? When we apply a unit step function as an input, we expect the output to become 1 eventually, or the output to respond in an efficient manner to the input. But if we decrease 1 by RC, or if we increase RC, which is the time constant, then this point goes further and further, and the response of the system becomes sluggish. So this is a trade-off. This is a fundamental trade-off, that if we want to have faster step response, we need a smaller value of RC, which implies that the filter will pass higher frequencies. As we have discussed several times in the class, everything comes at a cost. So this is the first cost we have to pay if we want to pass very low frequencies. But that does not imply that this filter cannot be used. This filter is used for very simple applications, very simple low-pass filtering applications. Let us explore the series connected RC circuit of previous example and now take voltage across the resistor V0. In the previous example, we saw that the circuit gave us the rough approximation of a low-pass filter. Over here, we'll see that when we take the voltage across the resistor, the circuit will behave as a high-pass filter. So once I apply KVL, this is the equation I get, and assuming that the frequency response of this filter is given by, or the circuit is given by G omega, this is the response of the circuit, frequency response of the circuit. The use of H or G does not make any difference. If G or J or G or H are a function of G omega, free order frequency. Generally, H is used for frequency response. Over here, G is just shown or used to illustrate the difference of the previous frequency response of the same circuit with this response. So once this response is plotted, it is seen that at 1 by RC or at 1 by tau, the filter's response starts to increase. We can say that 1 by RC is roughly the cutoff frequency of this response, and this is the phase response of the circuit. So once, if we look at the frequency response, we can see that at lower frequencies, the frequency response magnitude is 0 or low, and it starts increasing rapidly after a cutoff frequency. If we determine the step response of the circuit, this figure illustrates the step response. Now it is seen that once the value of RC is increased or 1 by RC is decreased, the circuit will take a longer time to reach the steady state. So if we increase RC, the circuit's response becomes sluggish, and this passband edge, it reduces. So to get a narrower response, to reject lower frequencies and get more passband frequencies, the response of the filter will become sluggish. This is the same compromise as we discussed in the previous case. When you are going to solve questions for this chapter or for this lecture, you are not going to deliberate on responses like this. This is just design factors which you as an engineer, as a designer, have to know whenever you're designing filter for a specific application. In your undergrad SNS course, you're not going to design filters, but it is important that you know these concepts so that you know that whenever you gain an advantage, there's a price to pay for that advantage. There must be some price No advantage comes without a price. So we have seen that a simple RC circuit can serve both as a low pass filter and a high pass filter depending upon the output voltage that across which element we are taking our output voltage. But we saw that the filter did not have a sharp transition from the pass band to the stop band and vice versa, because there was just one parameter. It was a first order circuit and it had just one parameter, which was resistance and capacitance, which controlled both the frequency response and time domain response of the system. So we can design more complex filters, and more complex filters will be implemented using more energy storage elements, capacitors and inductors. And after using more storage elements, the order of the differential equation will be higher. So a higher order filter will offer more flexibility in terms of characteristics. For example, it can allow a sharper pass band stop band transition, or we can have more control over the trade-offs between the time response and the frequency response. But we know that having a higher number of storage elements means that there will be more heat dissipation in the circuit, the cost of the circuit will increase, and so forth. So as I always say, there's a compromise between one thing and the other. We have seen that how continuous time filters can be described by differential equations. In a similar fashion, discrete time filters can be represented by linear constant coefficient difference equations. Such a representation is important because expressing a circuit through a difference equation simply implies that we have some delayed elements, delayed samples of the input signal available, and we multiply the delayed samples of either the input or the output by constant coefficients, and we get our output. So for discrete time systems, two distinct type of filters can exist. One of the filters has an infinite length of impulse response, and it is known as an infinite impulse response filter. Such an infinite impulse response exists from the fact that this filter, the difference equation of this filter, includes delayed samples of both the input and the output. Therefore, it is also known as a recursive filter. Recursion, as we discussed already, means to improve on something. So recursively, the filter tries by delaying the output samples and subtracting them from the current output, we are able to create a better output each time. There are filters where the output samples are not delayed and added to the input to improve the output. Such a filter will have a finite impulse response, or the length of the impulse response will be finite. So such a system is also known as a finite impulse response system or a non-recursive system. So firstly, we'll discuss recursive discrete time filters. A first order recursive discrete time filter can be described by the difference equation yn minus a yn minus 1 is equal to x of n, where x of n is the input, y of n is the output at current time n, and yn minus 1 is the delayed output or the output from the last instance. If we are taking the current instance at n is equal to 0, then this means that this output is the previous output, which is y of minus 1. We'll be developing this filter, or we'll be determining its frequency response in a similar fashion as the continuous time case. So we say that if input is x of n is equal to e j omega n, then by virtue of it being an LTI system, and this value being the eigenvalue, y of n will be h of e j omega into e j omega n, where h e j omega is the frequency response. So substituting the values, we get the frequency response h e j omega as 1 by 1 minus AE minus j omega. If we determine the time domain expression for this filter, it comes out to be Hn is a raised to power n into u of n, and step response, which is a convolution of the impulse response and the unit step function, comes out to be Sn is equal to 1 minus a raised to the power n plus 1 by 1 minus a into u of n. I'll pause for a second and just illustrate that this filter is just one of the first order discrete time filters that can exist. We could have a delayed input term over here as well, but this is just the simplest example of a first order filter that we are discussing. We are not fixing our coefficients to a value because we want to see what the change of coefficients what effect does the change of coefficients have on the frequency response of the system. The magnitude and phase of the frequency response for this recursive IIR filter are shown in figure. For this, drawing these figures, the value of A is taken as 0.6. It is observed for the value of A 0.6, or for all positive values of A, the trend of magnitude response is such that lower frequencies will pass without any attenuation. In fact, since the magnitude of amplitude is 2, they'll be a little amplified, and higher frequencies will pass with attenuation. So this trend can be said to be that of a low pass filter. So for positive values of A, the frequency response of the filter is that of a low pass filter. For values of A negative, that is, if we choose A is equal to minus 0.6, for such negative values of A, we can see that the response of the filter is such that lower frequencies pass with attenuation, or they are amplified less, and higher frequencies are in fact amplified. So this trend is that of a high pass filter. So a simple first order recursive filter can act as both as a low pass and a high pass filter depending upon the value of A. It is seen that for both these situations, the frequency response is plotted between minus pi to pi. This frequency response is also obtained in a similar way as the continuous time case. One varies frequencies from minus pi to pi, choosing an interval, and the magnitude and frequency of the response is plotted. For this recursive discrete time filter, the choice of parameter A also controls the speed with which the impulse response and step response reach their steady state values. If the value of A is small, the steady state value will be achieved earlier, or the response will be faster, and hence the filter will have a smaller pass band. So just as the case with differential equations, higher order recursive difference equations can be used to provide sharper filter characteristics. Higher order means that now the filter will have greater number of delay elements, or greater number of values which are being fed back to achieve the response. This also helps to provide more flexibility in balancing time domain and frequency domain characteristics. Time domain characteristics is how fast the response of the filter is, and frequency domain is how sharp the transition from pass to stop band is. And finally, we can notice that for the situation xn is equal to h of n is equal to a of n u of n, the system is unstable if the value of a is greater than 1, because now we have a rising exponential, and therefore the system, since the system is unstable, so it will not have a finite response to complex exponential inputs. Since Fourier based analysis techniques focus on stable systems, so we'll not analyze such a system and will restrict ourselves to stable systems only. The other form of discrete time filters is non-recursive discrete time filters. The general form of expression of such a filter is given by the difference equation. Y of n is equal to summation k varies from minus n to m, b of k, x of n minus k. As it is clear from this equation that for this filter there are no delayed terms of y being added on the left hand side of the equation, or there are no delayed output terms. Since there is no recursion, so therefore it is known as a non-recursive filter. From where it derives its FIR name is through its impulse response. If we want to determine the impulse response of this filter, we replace x by del and y by h, because that is what the impulse response is. When the input is an impulse, the output is the impulse response, and the impulse response comes out to be h of n is equal to k varies from minus n to m, b of k del n minus k. Now it can be seen that the length of the impulse response varies from minus n to m, or it is finite in length. Therefore, such a filter is also known as a finite impulse response filter. If we determine whether such a system is stable or not, so we know that one of the condition for stability states that h of n must converge. Since the value of h of n will always converge for a finite sum, therefore FIR filters or non-recursive filters are always stable. So the first example for such a filter is a moving average filter. It is one of the most basic examples of a FIR filter, where y of n is a moving average of all the samples which are being added. In this example, we are taking a 3-point moving average filter. So there are 3 samples, a current sample, a previous sample, and a future sample, which is being divided by 3. It is not necessary that you take a future sample. You can take 2 previous samples. So this filter shown, the equation shown is for a non-causal system, but y of n is equal to 1 by 3 x of n minus 2 plus x of n minus 1 plus x of n is for a causal system. So this simple filter is a 3-point moving average filter, and if we plot the frequency response of such a filter, it can be derived from h of e g omega is equal to 1 by 3 e g omega plus 1 plus e raised to the minus j omega, which is 1 by 3 1 plus 2 cos of omega, and plotting in a similar way as we have done, varying the values of omega from minus pi to pi, we can get the magnitude response as shown in figure. Although it is difficult to outrightly say what this response is, but if we look at it closely between 0 to pi, we can see that from 0 to pi by 2, the response has a higher value. It passes lower frequencies with little or no attenuation, might amplify, but the higher frequencies are suppressed. To such a kind of filter is known as a low pass filter, and in practice moving average filter is used as a smoothing or averaging filter to prevent high frequency transitions. Simply high frequency transitions or high transitions can be removed if we average out the value, because normally we also know that whenever we take an average, an outlying value averages out in the average. Non-recursive filters can also be used to form high-pass filtering options. So an example of such a filter is y of n is equal to x of n minus x of n minus 1 by 2. The order of this filter is 1. If we determine the impulse response, we simply for the impulse response replace x of n by del of n. This is the impulse response, and the frequency response is shown. So when we plot this frequency response, we can see that this frequency response can be categorized as a high pass filter response, because for low frequencies we have 0 amplitude for h of eg omega, and for higher frequency the amplitude increases. So this is crudely a high pass filter response. So summarizing our discussion for non-recursive or FIR discrete time filters, we have seen that the impulse response of such a system is of finite length. Therefore, it is always absolutely summable for any choices of pk, and all such filters are stable. Also, if this value of n is greater than 0, which means k is equal to starts from negative values, this means that y of n, the output, will depend upon future values of the input. Such a system will be a non-causal system. But for some applications, such as applications where the data stream is already recorded, such as if you have already recorded sound or an image, causality is not a necessary constraint, and thus we can freely use such filters. However, in many applications, such as those in real time, where you want to have the output as soon as the input is ready, causality is essential, and for such cases we must take n is less than equal to 0, or the lower end of the summation sign starts with a positive value. Minus minus n becomes plus n. Summarizing the chapter is this slide, where we have discussed Fourier series in both continuous and discrete time. We have seen that any periodic signal can be expressed through a sum of harmonically related sinusoids, and we have also seen one of the most important applications of signal processing, which is filtering. This concludes lecture 30. For this lecture, you have to go through book examples 3.16 and 3.17. Example 3.16 is done in this lecture, and example 3.17 you'll do yourselves. Numerical problems 3.13 to 3.20 and 3.24 to 3.30 of the textbooks are to be done for practice. For this lecture, you're also given an assignment, which is a graded assignment having 25 marks maximum. This is an individual assignment and will be checked whether you have copied amongst your classrooms or not. So please be careful and submit assignments independently without taking material or help from your class fellows. The deadline for submission of assignment is 5th June 2020. You can take extra time if you want till the end of June, but I will suggest that you start doing this assignment as soon as you cover today's lecture 30, because the lecture is related, or the assignment and the lecture are very related. Also, because for the final section of our course, I'll also be giving you an assignment which will be graded as well. So if you work on the assignments in parallel whenever you study the text, it is going to be useful for you. Finally, the paper submission deadline is extended to 15th June 2020, since university is not opening after Eid. So you can take 15 extra days and work on the paper. I'll advise you to work on the paper, start early, because if you prolong it till the end, it might not be a good paper, or it might not cover all the details you wanted to cover. So be proactive and start working on the paper early on. That's it. I wish you all the best. See you in 2 weeks' time. Allah Hafiz.